All right, last time we started section 4.3 and we looked at the greatest common divisor, and today we're going to look at least common multiples. So we're going to flip through to where we were. You're going to see a lot of repeats from last time in terms of methods for actually finding this. So a least common multiple is the least non-zero whole number that is a multiple of all whole numbers in your set. Okay, last time when we started with greatest common divisor, I kind of pinpointed the fact that the first and foremost description in that phrase is divisor, which means we're dealing with small numbers. That is, numbers that are typically smaller than what you start with. Same thing's going on here. The most important word in what we're describing here is the word multiple. So if it's a multiple, it's got to be at least as big as or bigger than all the numbers that you're working with. Okay? So the fact that it's the least simply means that it is the least of something that's already big. All right, these are larger than you're dealing with originally kind of numbers, whereas divisors are smaller than what you're dealing with numbers. So we're going to work on several different methods of finding the least common multiples. And the first one we're going to work with is called a number line method, or sometimes called the colored rods method. So in this method, we're going to show multiples of all numbers on a number line in the intervals of each value, and then find the first value at which the intervals coincide. Okay, so this is similar to the earlier things that we were doing with greatest common divisor, wherein it really only works for values that are kind of small. I mean, if you had to do this for very large values or values that don't hit on a least common multiple pretty quickly, this particular method is really annoying, is what it really will be, okay? So again, not all my methods work equally well for all sets of numbers, but I want you to know that there are lots of ways in which to do these. So let's take a look at an example of this one with the numbers 6 and 15. So the way that this looks is that you start with a number line, and we'll start with 0 on my number line. And it says that I'm supposed to use the number 6. So I'm going to do it on a number line, and I'm going to talk about the colored rods description part of this. So if I mark out 6 on the number line, and I sort of jump 6, and then I jump 6 more, where will I land? 12. And then I would land at 18. And I would keep going, right? I'm going to make this keep going in just a second. The other number is supposed to be 15, though. So I'm going to do the same thing with 15. So if I go from 0 to 15, I'm jumping all the way over to here, between 12 and 18. And you can see that if I go 15 more, I've exceeded where my number line is actually currently going. So I'm going to just make my number line a little bit smaller so that I have more space. And we'll try to make it continue. So if I continued my number line for 15 more, I would be at, this is probably not quite right in terms of visually, but 30. That's not too bad. But I'm not there, that is, all the way to the 30 yet. 15 wasn't a coinciding place for them to both land, the arrows to both land. So after 18 in my multiples of 6, where would I be? 24? So here's to 24, and then after 24, where would I be? 30. So I do eventually land at the same value when I take my jumps. You can kind of think about this as like skip counting, right? You're skip counting until they coincide. You're making these jumps along the number line until they coincide. It talks about, well, let me write down the answer for this one before I describe the other version of this. The least common multiple here then is 30. And you notice 30, of course, is larger than either the 6 or the 15, so that makes sense. All right, so it talks about the colored rods method. We don't have any in our department, but there are colored rods that represent integer values. So you have these sort of manipulatives that look like it's 1 unit long and a different color that's 2 units long and a different color that's 3 units long and a different color that's 4 units long. And they change them based on the color. And what you can do is you can like put the blocks side by side until the blocks are the same length. So visually it looks something like this. If you were doing this idea with my 6s, then you would have it's a little thick. I'm going to make it a little bit thinner. You would have, I'll do it below the graph, a blue rod that's 6 long, and another blue rod that's 6 long, and another blue rod that's 6 long. And you keep lining up all of the rods, side by side, these long blocks. And in the same token, by the same token, you do the same thing with the blocks that are of length 30. So you line up, or not 30, 15. So you line up a 15 block, and it looks something like, okay, that was bad. Again, looks something like that, right? And then you line another 15 block right beside it, and it looks something like this. And eventually, the lengths of blocks stacked side by side measure the same length. And the full length that you would get is the least common multiple, so it would be 30. So that's why this is also called the colored rods method, is because there actually are manipulatives that do this. Okay? Now, obviously the manipulatives that do this don't encompass every possible value, right? I mean, like, I can only have so many different colored rods. So again, I'm limited in what I can use this for, but it works really nicely. It's a hands-on kind of concrete model when you're first talking about these. So they work nicely. The next one is another one that works well for small sets of numbers, or sets of small numbers is what I meant to say. What you do is you list, this shouldn't say all, because you can't list all multiples. It should say list many multiples, a long list of multiples of each value. And then you find the least value that the lists have in common. So this is almost like when you're in, second, third grade, and you're looking at your multiplication tables, and you learn, again, to skip count, right? So I've got 3, 6, 9, 12, 15, 18, like that. Okay, and you just list them all out. Okay, so I don't have to list that 1 times 3 is 3, and 2 times 3 is 6, and 3 times 3 is 9. That's not what I'm doing. I'm just listing the result of what happens when I have my multiples list. And then I look at the list that I'm using, and I look for the one where they coincide first. Okay, the least multiple of the lists. So we're going to use 12 and 15 to do this with. And we're going to start here with 12. So if I'm listing my multiples of 12, I will start with 12. What would come next in my multiples list of 12s? 24. And then 36. And then 48. Let's list 3 more. Okay, and we'll stop there. So there's not really when do I stop? There's not an answer to that question. You simply list some of them out, and you're going to do the same thing with the other list. If you find one they have in common, then you're done listing. And if you don't, you keep your list going until you do. Okay? So this will keep going. This will be enough on this particular one, so I'm not going to need to keep going. But if I did, I could. And then we're going to do the same thing with 15. So I've got 15, and then what? 45. Okay, and I can actually stop here. Why? Because they have 60 in common, right? So, whoops. Oh my goodness, try that again. So at this point, these match. And once they match, we're done. And we've found what we were attempting to find. So the least common multiple is 60. Okay, now can you imagine, though, if it wasn't 60 and you had to keep going? And if you kept going and you still didn't find it, and you just had to keep going and keep going until finally, at some point, you would get to 12 times 15, which is a pretty large number. That's as far as you'd ever have to go for sure. But it could get really large really quickly, and 12 and 15 aren't big to begin with, right? So this method, either of these methods, doesn't really work well if the numbers don't have anything in common pretty quick. So what do we do when we don't have that option? Well, we've got a few other options. So we saw last time a prime factorization method. So when we did this before, several of these steps are identical, and some of them are slightly different. We constructed the prime factorization of each number. We looked at the prime factors in each factorization. Before, we chose only the ones they had in common. On this time, we choose all of them. So even if they have things that are not in common. And then we list each prime number with the largest exponent instead of the smallest exponent in either number set. And then we find the product by multiplying it out. Okay, so there's some slightly different pieces that change the results quite a bit. Listing all prime factors and using the largest exponent. Those two pieces are going to drastically change what we end up with. So we'll do an example with 90, 50, and 20. So there's nothing special about the fact that there's 3 numbers, but we can do it with 3 numbers, so I want to show you how that looks. If you do it with two numbers, it's fine. It works the same way. But we're going to find our prime factorization, and we're going to do that. I'm going to do it with that division algorithm that I did before where we divide by primes. So I'm going to divide 90 by 2, and I get, and 45 doesn't divide by 2, but it does divide by 3 to give me 15, which divides by 3 again to give me 5, and I'm done. There's no more primes there. So this is 2 to the first, 3 squared, and 5. That's 90. Now we're going to do 50. So 50 divides by 2 to give me 25, which divides by 5 to give me 5. So on this one, we have 2 to the first, if you wish, times 5 squared. And the last one is 20, which divides by 2 to give me, 5. So on this one, I have 2 squared times 5. So these three factorizations at the end is where I am now. And I need to list all of the prime numbers that are bases as part of my answer. So my LCM will include all the prime numbers. So what are my prime numbers that are bases? 2 and 5, right? Doesn't have to be the ones that are in common only, but anything that they have in any of the three sets of numbers as a prime base. And then I want to find the largest exponent. So what is the largest exponent that you see on 2 in any of my red squares? A 2. What is the largest exponent you find on the 3 in any of my 3 squares?
2.
Happens to be a 2. And the largest exponent you find on the 5 in any of the 3 squares?
2.
A 2. So of course they're not always all 2s. This one just happens to be. And we're going to multiply this out. So let's see, I have 4 times 9 times 25. So if I multiply 4 times 9 times 25, what will I get? Grab a calculator if you wish. It's totally fine.
Nine.
900 is right. The least common multiple of 90 and 50 and 20 is 900. Which is kind of crazy because that's a really big number compared to the 90, 20, and 50 I started with, which are really not all that large. So can you imagine if you had to write out multiples of 20 until you got to 900? Oh my word, you might just quit, right? You would just be like, I don't even care. It doesn't matter anymore, right? It would take a really long time. All right, we mentioned this method last time too, and in fact I told you I like this method really a lot because it seems to take that prime factorization method and make it faster. So the division by primes method puts all the numbers in a row, divides each of the numbers by a common prime factor. So it has to be a common prime factor. And then you divide all of those values by another common prime factor. So in order to be common, it has to be common to at least 2 of the numbers. So if I'm going to do an example with 3 numbers here in a minute, you'll see what I mean. And we keep repeating until there's no more common factors. And then the LCM is the product of the primes. There's actually a typo here. Primes. It's actually in final quotients. You'll see what I mean. Okay, so we're going to do 90, 120, okay? So we're going to write the numbers side by side. 90, 120. All right. Did everybody have the ones from the previous slide? Do you mean to go back? You got it? Okay. All right, so we have 3 numbers. If we had 2 numbers, it'd be fine. We could do just the 2 numbers. But I need a number that divides all 3 numbers if there is one. Is there a number that divides all 3? 2 will do it. So we're going to divide all of them by 2. So I'm going to get 45, 50, and 10. Everybody good so far? Okay, cool. Now I have 3 more numbers. I'm looking at 45, 50, and 10. I need a number that divides all 3 numbers. A 5. So I have 9, 10, and 2. Okay, if I were doing greatest common divisors, you know, the stuff we did on Wednesday, the answer would be 2 times 5 is 10, because there are no other numbers that divide 9, 2, and 10, all of them, right? Y'all with me? Okay, so if this were a greatest common divisor question, we would be done. The answer would be 2 times 5. But it isn't. This is a least common multiple question. So here's the difference. I take a look at 9, 10, and 2, and I ask myself, are there any numbers that divide at least 2 of them? And the answer is yes, and Taylor's right, it's 2. So the one that doesn't get divided, the 9, just comes down, and I kind of ignore that it's not divisible by 2. It won't hurt anything, okay? And I divide the other 2 by 2. So I end up with a 5 and a 1. Now, 9, 5, and 1, do they have anything that divides any pair of them? No. So here's the cool thing, again with division of primes, just like from when we did divisors, the answer is the multiplication of everything that's remaining on the outside. So these are the primes that it referenced. These are the quotients that I sort of wrote in accidentally at the bottom of the screen. I said, oh yeah, and it should say and quotients, that part. Yeah. So we're going to end up with my answer being that the least common multiple is 2 times 5 times 2 times 9 times 5. And just for good measure, I'll go ahead and write down times 1, although it does not really affect anything. And then you're going to multiply it out. And what do you get for this one? It ends up being 900 as well. Slightly different set of numbers, still has the least common multiple of 900. Okay, so it should come as no surprise to you that there must be some sort of a relationship between greatest common divisors and least common multiples, because the methods that I'm using are really similar, right? Like I stopped short and I said, hey, look, your GCD is right here, but if I go a little bit further and make this little tweak, then I've got the LCM, right? There's definitely a relationship between the two, and this is it. When you multiply the greatest common divisor times the least common multiple, you get the product of the numbers. Okay, so this part right in here is not talking about multiplication. This is telling you just that it's referencing the numbers. You want the greatest common divisor of 5 and 7, or the least common multiple of 5 and 7, and then you multiply 5 and 7. Okay, so those are just a reference point telling you its greatest common divisor or least common multiple of what. So the cool thing is, if you know one of them, you can find the other one without having to recreate the wheel. That's pretty cool. So it only works, however, for 2 non-zero values. So my last example where I had 3, I wouldn't be able to use this theorem on it. It wouldn't work. It only works for 2 numbers, okay? So we're going to do an example where we go back to something from last time. Last time we had example 4. So flip back over to example 4, and I'd like for you to find for me the greatest common divisor on example 4 of the numbers 72 and 126. And we found it using the Euclidean algorithm.
18.
It was 18. All right, thank you. Okay. So what this formula says is that the GCD times the LCM should equal 72 times 126. Okay? And we know the GCD, it's 18. Okay, so this is what we've got. We know our 2 numbers. We know the GCD. The only thing to find is the LCM. How would I do that with this equation set up?
Multiply it out and find the 18.
Right. I need to multiply the 72 and the 126. And then I need to take that value and then divide by the 18 that's over here on the side of the LCM. So what is 72 times 126 divided by 18? 504. That would be my LCM. 504. It's good stuff, right? I don't have to recreate it. I don't have to find it again. If I found one, I can find the other kind of with a shortcut. So those of you who end up presenting or potentially presenting this section of material, either the greatest common divisors or the least common multiples, you're going to create word problems. And so far I've shown you no word problems in this section, right? So I'm going to give you a couple examples of some context questions, some word problems that relate to these ideas. All right, so here's the first one. There's a lot of conditions in order to make this true. Two bike riders ride around a circular path. So imagine them going around a park or going around a track and field track, okay? So they're just going around and around and around. The first rider completes one round in 12 minutes. Maybe they're going around a lake. Okay, no shortcuts through the lake. And the other one can complete that same lake round or that same circular path in 15 minutes. Okay? So we want to know if they both go, if they start at the same place in the same time, it's like a race, right? Starting at the same place in the same, they got to go in the same direction. Otherwise, they keep crossing paths. For those of you who ever walk the track at the rec center, right? There's a reason why they make you go the same way, so that you're not constantly running into people, right? Okay, so they go the same direction, and they have to go the same pace. So like they can't speed up and slow down, or this isn't going to work either. All right, so this is we can't do this infinitely many times because eventually they get tired, right? So this is not a process that can be repeated forever, but for a little while. The question is then after how many minutes will they meet again at the starting place? Now they might pass one another along the path in the middle of the path somewhere, but the question is when do they get back to the starting place? So if you can sort of picture if you were to string our track out in a line, kind of like I did at the beginning here. This is an LCM question. I want to know when the 12 minutes and 12 minutes and 12 minutes and 12 minutes finally end at the same point that the 15 minutes and 15 minutes and 15 minutes and 15 minutes end. Can you picture that happening? So as you're looking at these problems in this section, you're going to have to figure it out. Am I working with something that's a GCD problem? The next one is, and I'll show you what it looks like. Or am I working with something that's an LCM problem? And this one right here is an LCM problem. It's a least common multiple. Because what I'm wanting to do is I'm wanting to continue this process with these bike riders going again and again and again, multiplying out their 12 minutes and their 15 minutes. So I want to find the least common multiple of 12 and 15. And nobody told you how you have to do it. So what would you like to do to find this solution? Do whichever method you want to do. Which one do you want to do?
We already multiplied, we already found the least common multiple.
Did we do that one already? We did that on the second one, didn't we, with our lists? Okay, so let's do it a different way then so you can see that it works out the same way. How about we do division of primes? That's my favorite anyway. Are you good with that? Okay. So if we did 12 and 15 with division of primes, we would look for a number that they have in common. 3, right? 3 is the first one. And I would get 4 and 5. How about 4 and 5? Nope, nothing else. So my answer is the multiplication of 3 times 4 times 5. And 3 times 4 times 5 is what? Yeah, it's 60. And the problem is in numbers of minutes, so it's after 60 minutes. Okay? Yes, ma'am.
So question, if we do this
Mm-hmm.
with all the problems, couldn't we just say that 3 times, couldn't we find the least common multiple and the greatest common divisor in the same
Yeah,
thing?
absolutely. Yeah,
Because
the
you
greatest
can
common divisor would be 3 on this one. Exactly. But if you answered 3, in this context, it wouldn't make any sense, right? They meet up again after 3 minutes. Well, no, they don't. After 3 minutes, they've barely run any or biked anything, right? And they're certainly not at the same place at the same time. So you have to make sure you're answering the question that's really being asked. Yeah. Yes, ma'am?
The key word in that, knowing its least common multiple is will they meet again?
Well, in the sense that they're repeating a pattern, yeah, that would make sense. Let me show you another example of one that's a GCD, because they feel so different. The problems do not feel alike at all. Let me show you the example. I use this one because it's cupcakes. Dr. Hands makes cupcakes for her students. Sometimes, right? Yeah. She makes 20 chocolate cupcakes and 24 vanilla. She wants to display them on plates with the same number of cupcakes on each plate, but only one type of cupcake on each plate. Okay, so if you start intermixing the chocolate and vanilla cupcakes, you lose the ability to actually have the 24 and the 20 independently divided. So you have to keep all the vanilla together, you have to keep all the chocolate together, okay? Does that make sense in order for this problem to actually be GCD? Yeah, I mean, otherwise, if I just add them all together, I could divide by anything that it's divisible by, and it would be working, and it might not divide either of the numbers that I started with, okay? So be careful about that. What is the greatest number of cupcakes she can put on each plate? So we do want to divide them up, and you almost see that making sense, right? It says you want to take the cupcakes and you want to split them apart, right? That's not happening in my last problem. Another example that they do in your book of a least common multiple is the colors on the radio. You know, this number color gets this prize and this number color gets this prize. What's the first number color that gets both prizes? Because they happen to hit the least common multiple of both of those things. That's another one. Your book does some other GCD ones as well, but they all have to do with taking objects, I think, and splitting them apart. So you'll know they're talking about divisors, okay? Okay, so I need the GCD of 20 and 24. And we just did division of primes, so let's not do division of primes again. How else might you want to do this one? How about we just list them out? Let's do that one. So if I do 20, what are the numbers that multiply together to give me 20? I'll start with 1 and 20. And then what? 2 and 10, and 4 and 5. And I'm done, right? There's no other options. Okay, let's do the same thing with 24. So again, I'm going to start with 1 and 24. What else? 2 and 12.
4 and 6.
Okay, so a greatest common divisor. These are all divisors. I need the greatest number in the lists that match. 4 is it. You got it. 4 is the biggest number in both lists that matches up. So think with me, if you really had 20 cupcakes, could you put 4 on a plate and evenly put all the cupcakes on a plate? Yep. Could you do that with your 24 cupcakes? Yep. Are you going to have more plates of one than the other? You are. You can't fix that, but you don't have any cupcakes not on a plate. That's your goal. Your goal is that all the plates have the same number of cupcakes with none left over. You can't have just straggling cupcakes out there. You don't get to eat any in the process. That's not allowed either. Yeah. Okay, so the answer to the question, it says, what is the greatest number of cupcakes she can put on each plate? And the answer is 4. 4 cupcakes. Sorry, let me get the word cupcakes on there. 4 cupcakes per plate. Anything more than that would leave leftovers, and there's no leftovers allowed for this to work. Any questions on that? Okay, we have like 18 minutes or something like that for group work, so I don't know, I can't remember how long the group work actually is, so maybe you'll get done early today. I sure hope so, for you and me both. But go ahead and find your people and take a look at the next group work activity.